I know, it's the moment you've all been waiting for, the moment you get to graph logs. Because we all love graphing, right? This one's for you, Donnie. Okay, so before I talk about graphing logs, I want to talk about inverse functions a little bit, and you'll see why in a moment. But inverse functions can be found if we just switch the x and y values of a function, and it also is the reflection of the original graph. The inverse function is a reflection of the original graph over the y equals x line, like this. So if I have 2 to the x here in blue, right there, now black, if I reflect it over this line right here, then I have the log base 2 of x, because that is the inverse function of the exponential 2 to the x. So the general shape of a logarithmic graph, when our a value is greater than 1, a would be the base of our log here, so we have log base a of x. It has this shape here, right? Okay, so it's always increasing. Its domain is 0 to infinity. Its range is all real numbers, and it has a vertical asymptote here at x equals 0. And then if I have a base on my log that is less than 1, then it looks like this instead. So if I have, for instance, log base 1/2, well, then it decreases like this. The domain is still 0 to infinity. The range is still all real numbers, and the vertical asymptote is still x equals 0. All right, so let's get ready to graph logs. We have this equation, y equals log base 2 to the x, and I want to start by finding the inverse function. So I'm going to switch the x and y values around, and then I want to solve for y. And if you look here, I have log base 2 of y. I need to undo this log base 2. So I'm going to give it a base of x, and y equals 2 to the x. And if I make a table of values here, I'm going to just throw a few values in here, small ones, because remember, exponentials grow really quickly. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. The reason I'm doing this is because I can now find f inverse of x, or points of f inverse of x. I just need to switch my x and y values around. So I'm going to take my y values here and move them over to be my x values here. And that means these are my new y values. My old x values are my new y values. There is f inverse of x. And the original function now is 2 to the x equals y. That means that I have the points for this graph. So when x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. And when x is 4, 1, 2, 3, 4, y is 2. Hey, if I pick carefully, I could find another point on this graph. How about 3? If x is, oops, wrong spot. If x is 3, what's y? Yeah, that's right, it's 8. So I have another point even. And looking at the general shape of the graph from before, since my base is bigger than 1, it's going to increase instead of decrease. All right, here's one for you to try. Pause the video when you're ready to check your answer. Start it back up. Okay, so we have y equals log base 3 of x. Let's switch our x and y around. I need to get rid of this here. I'm going to give it a base of 3 because 3 to the log of 3, base 3, sorry, not log of 3, is 1. So I end up with y equals 3 to the x. And if I make a table of values for this function, (3 to the negative 2 would be 1 over 9. 3 to the negative 1 would be 1/3. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. And then I'm just going to switch the x and y values around. So 1/9, 1/3, 1, 3, 9. Okay, when x is 1/9, that's really close to 0, but so this one gets super close to 0, but never gets there. When x is 1/3, y is negative 1. When x is 1, y is 0. Any exponential function that doesn't have any transformations on it, or log function that doesn't have any transformations on it, I should say, is going to have a point at 1, 0. All right, and then I have a point at 3, 1, and a point at 9, 2. And that's it. That's how you graph an exponential. Okay, for our next example, we're going to do something a little bit more complicated. Everybody loves natural logs. Just kidding. That's why we're going to graph one. So I'm switching my x and y values around, and now I need to solve for y. Because I have a natural log here, this is all in parentheses. I can't do anything with that until I undo the natural log. And then inverse of a natural log is an exponential with a base of e. So if I give both sides an exponential base of e, that's going to get rid of this. So e to the x equals y minus 2. That means that y is equal to e to the x plus 2. All right, let's make a table of values. So if I do small numbers, negative 2, negative 1, 0, 1, and 2, and I put that into my function here, f of x, then I get 1 over e squared plus 2, 1 over e plus 2, 1 plus 2, e plus 2, and e squared plus 2. Now, as much as I love these numbers because they're exact, they're not really very much use when I'm trying to graph them. But don't get me wrong, I love these exact answers. So we're going to put them into a decimal approximation, and we're going to switch the x and y values around. So 1 over e squared plus 2 is about 2.1. 1 over e plus 2 is about 2.4. 1 plus 2 is, of course, 3. E plus 2 is about 4.7. And e squared plus 2 is around 9.4. And then I just take and move my x values over to my y values. And I'm going to graph it. 2.1, when x is 2.1, y is negative 2. That's over here. When x is 2.4, y is negative 1. When x is 3, y is 0. When x is almost 5, y is 1. And when x is almost 9.5 actually, y is 2. Look at that. it looks like my asymptote is at 2. And if I look at my original function, this would be a horizontal translation, 2 to the right, and sure enough, that's what's happened here. If I wanted to plot important points, and you should, anything that's works out to be a whole nice number, you should plot. In this case, it'd be 3, 0. That's a helpful point to know. So here's one for you to try. Pause the video and restart it when you're ready. All right, let's switch our x and y value around. You'll notice that I was nice to you and I left you one that was a little bit easier. I'm going to subtract 1 from both sides, so I get x minus 1 equals the natural log of y. And then I need to get rid of the natural log, so y, if I give both of these a base of e, is going to equal e to the x, but this time the minus 1 is in the exponent. Okay, so let's make a table of values. -1, 0, 1, 2, and 3. And I'm doing that because if I subtract 1 from my exponent every time, then that's going to shift all of these numbers. So e to the -1 minus 1 would be 1 over e squared, because that'd be e to the -2. And then e to the 0 minus 1 would be 1 over e. E to the 0, e squared. And, oh no, e to the first, sorry, and then e squared. All right. Let's get a decimal approximation and switch the x and y values around. 1 over e squared was about 0.14. One over e was about 0.4. E to the 0 is simply 1. So I have a point here at 1, 1. E to the first is 2.72, and e squared was 7.4, I believe. All right, let's plot our points. So around x, just around 1/10, but really hard to tell, it's going to look like that. And almost 1/2, it's going to be 0. And then I have a point at 1, 1, a point at 2.72, so somewhere around there, 7.4, that's around here, so 3, I go up to here, there's my asymptote. What would be the important point to label here? 1, 1. I don't have any other really nice points, so that's about all I can do. All right, one more example for me, and then one more for you to try. So here I have a few more transformations applied, so I wanted to practice that. Let's find the inverse function first. All right, so we can go ahead and add 1 to both sides. And then I'm going to go ahead and give both sides a base of 2, and I get 2 to the x plus 1 equals 2y. And then I'm going to divide both sides by 2. By the way, that's 2 to the first. So y equals, I have the same base here. I can go ahead and subtract the exponents. X plus 1 minus 1 is just going to leave me with x. So y equals 2 to the x. And we've already graphed this one, but let's go ahead and do it anyways. 2 to the 0 is 1. So I have a point at 1, 0. Two to the second is, well, let's do 2 to the first. 2 to the first is 2, so I have a point at 2, 1. 2 squared is 4, so I have a point at 2, 4. Sure, that's starting to look very familiar to you by now. You should at least label 1, 0. And another important point to label, because it would help you find the equation if you only had the graph, would be 2, 1. All right, give this a shot. This is the last example. When you're ready to check your answer, restart the video. Okay, so let's switch our x and y value around. All right, so 1/2 y plus 2, go ahead and subtract 2 from both sides. All right, we need to get rid of the natural log now because we've isolated it. And we get e to the x minus 2 equals 1/2 y. Multiply both sides by 2, and I get y is equal to 2 times e to the x minus 2. Let's make a table of values. All right, and then I'm going to use the values -1, 0, 1, 2, and 3. Take a minute. If you can't figure out why I've done that, take a minute and figure it out. It's an important skill. So when I plug in a -1, I get 2 times e to the -3. So that's 2 over e cubed. When I plug in a 0, I get 2 over e squared. A 1 would be 2 over e. A 2 would be 2 times e to the 0. And a 3 is going to be 2e. And when I calculate values for that, I get about 0.1, 0.2, 0.4, 2, and 5.4-ish. All right, so let's switch our x and y values around. Run out of room over there, so 0.1, 0.2, 0.4, 2, and 5.4. Darn, none of those worked out nice. But -1, 0, 1, 2, and 3. Oh yeah, 1 did. Let's start with that one, 2, 2, and that's the one I would label. All right, and then 0.1 is -1, so that's about here. 0.2 is 0, about there. 0.4 is 1, that's about there. Oof. And then 5.4 is 3. And that's all there is to graphing logs. Be ready to practice in class next time. That's a threat.